everyone and welcome to video number 6 in the 3-phase circuits course, 3-phase power. But before we start, let me remind you about the single-phase power. If you follow my channel and my videos, I introduced the single-phase power in 2 videos before. One of them is Induction Machine Course Chapter 0, Video 2, AC Circuits and AC Power Review. And the other one, in this course, why 3-phase systems outperform single-phase, and I used MATLAB Simulink to confirm this fact. I'm going to add for you in the comments the links for these videos. But we are going to have a quick refreshment about single-phase power before we start the 3-phase power. For the single-phase power, we have 3 types: active, reactive, apparent. Active is power P in the units of watt, reactive Q in the units of var, apparent S in the units of volt ampere. If we have a single-phase circuit or single-phase network with the voltage V of t, I of t, so definitely you are going to have this power triangle P, Q, and S. I'm assuming here that the current is lagging the voltage by angle phi, so this is why I put in this triangle positive Q. If the current is leading, we should put negative. I'm assuming now we have a lagging power factor, so we have P, Q, and S. So how to calculate the power P? Instantaneous power. So we proved that one before. P of t equals Vrms Irms multiplied by 2 terms. One of them with double frequency component, so we have a waveform with 2f, and the other one is a constant value, which represents the average power, where P equals Vrms Irms cosine phi. We can calculate Q and S as well. Q equals Vrms Irms sine phi, and S equals Vrms Irms. But now we're concerned with the active power P, and we are going to compare the 3-phase power with single-phase power. And later on, I'm going to show you how we can calculate Q and S. What we want now to prove why 3-phase power outperform the single-phase one. Let us see. In the 3-phase system, as we saw in the previous videos, we have 3 voltages, 3 currents shifted 120 degrees. We have VA of t, VB of t, VC of t. And the currents here is lagging the voltage by a certain angle phi. Here I'm assuming again that the current is lagging the voltage, but the current can be leading the voltage as well. In this case, definitely you have the same power triangle P, Q, and S. And P is the active power in watt, Q is the reactive power in var, and S is the apparent power in volt ampere. So we are concerned with the active power now. So how to calculate the instantaneous power? So similar to the single-phase system, P of t equals V of t, I of t. So we are going to do the same procedure here, multiplying the voltage, for example, of phase A by the current of phase A, plus the voltage of phase B multiplied by the current of phase B, and the same for phase C, and taking the sigma for these values. Now we can calculate the instantaneous 3-phase power by adding the power of phase A to the power of phase B to the power of phase C. And let us substitute by current and voltages. So P of t equals VA of t, IA of t, plus VB of t, IB of t, plus VC of t, IC of t. So let us identify the voltages and currents. So V of t, for example, equals V maximum sine omega t plus delta. And definitely VB of t and VC of t are shifted minus 120 and plus 120 from this delta. Delta is taken from the reference. The reference is 0 angle. And for the currents, I of t equals I maximum sine omega t plus theta. Theta is from the reference as well. So definitely IB of t and IC of t are shifted minus 120 plus 120 from this theta. So let me remind you about the trigonometric identities. If we have sine omega t plus sine omega t minus 120 plus sine omega t plus 120, that one equals 0. And the same for cosine function. And also if we have sine x sine y, we can write it as half cosine x minus y minus cosine x plus y. So now we are going to substitute in P of t. So in this case will be P of t equals V maximum I maximum as a common factor, sine omega t plus delta sine omega t plus theta, and another 2 terms shifted minus 120 and plus 120. So if we consider omega t plus delta is x and omega t plus theta is y, we can use trigonometric identities as we can see here. Sine x sine y equals half cosine x minus y minus cosine x plus y. So we can write sine omega t plus delta, if that one is x, that one is y, equals half cosine omega t plus delta minus omega t minus theta minus cosine omega t plus delta plus omega t plus theta. So let's simplify this one. So this one is going to cancel this one, and that one will be added to this one. In this case, we are going to take V maximum, I maximum over 2 as a common factor, will be cosine delta minus theta plus cosine 2 omega t plus delta minus theta. And we have another cosine delta minus theta for the phase B, and for phase B will be shifted minus 120, cosine delta minus theta, and another one plus 120 for phase C. Let's rearrange the equation. So in this case, if you remember, cosine omega t plus cosine omega t minus 120 plus cosine omega t plus 120 equals 0. So these terms are going to cancel each other. So we end up by P of t equals 3V maximum I maximum over 2 cosine delta minus theta. And we can say that phi, which is the impedance angle in this case, or the power factor angle, equals delta minus theta, which is the voltage angle minus the current angle. So we can write that one as P of t equals 3V maximum I maximum, and instead of 2 will be root 2 cosine phi. So in this case, VRMS equals V maximum over root 2, we call it V. RMS equals I maximum over root 2, we call it I. So we end up by this expression, P of t equals 3 VI cosine phi. What a fantastic results! So the power in time is a constant, which is now outperformed the single phase. In the single phase, we have oscillatory term by double frequency component. But this is the average power in time as well, will be a constant value. Let us take some hints and some comments about the three-phase power. P equals 3 VI cosine phi. So the values V and I are RMS values and phase values of phases A, B, or C. Comment number 2. The angle phi is the angle between phase voltage and phase current. So that one will be delta minus theta, which equals phi. So in this case, phi is the load angle or impedance angle if we are in the load side, or the angle between phase voltage and phase current if we are in the source side. Number 3. The angle phi is the angle between VN phase voltage and IA phase current. I'm assuming here that we have star phasor diagram, so that one is angle phi. You should find the same angle phi between VBN and IB and the same angle phi between VCN and IC. So phi, phi, phi. Comment number 4. The cosine phi term represents the power factor. If the power factor is lagging, the load current lags the load voltage by angle phi. If the power factor is leading, the load current leads the load voltage by angle phi. The same concept applied to the source side. If the value VRMS equals V phase equals V, and the IRMS equals I phase equals I, for star connection, the line voltage V line equals root 3 V phase equals root 3 V. And the line current equals phase current equals I. So I can say that 3V phase, I can write it as root 3 V phase, which is root 3 V line. So the expression can be written as root 3 V line I line cosine phi. For delta connection, the line current I line equals root 3 I phase equals root 3 I. And line voltage equals phase voltage equals V. So I can say that 3I phase, which is root 3 I phase. So that one will be root 3 I line. So I can write the expression as root 3 V line I line cosine phi. So we can calculate the power as 3V phase I phase cosine phi, or root 3V line I line cosine phi, respective of the connection, star or delta. As I mentioned, both expressions are valid for star or delta connection, but there is a certain limitation on this expression. I'm going to explain it now. The angle phi in both expressions is the angle between phase voltage and phase current. So the angle phi is the angle between phase voltage and phase current, which is delta minus theta. The angle phi in this expression is the angle between phase voltage and phase current, not the angle between line voltage and line current. So in both expressions, the angle phi is the angle between phase voltage and phase current. The last comment. These two equations indicate that the instantaneous power is always constant in time rather than pulsating, as in the single-phase case. Therefore, power delivery from a three-phase voltage source is very smooth, which is another important reason power is generated in three-phase form. And in case of single-phase, you have a double frequency component, so the system will be more noisy. And this is one of the reasons why the three-phase system is outperforming the single-phase one. Now we covered the active power P, which is in watt. So what about the reactive and apparent power? So let us put the expression based on this power triangle PQS. So we know that's phi equals 10 inverse Q over P. Please don't forget the brackets. So in case of the active power P, we can write it as 3 V phase I phase cosine phi. Root 3 V line I line cosine phi. Phi is the angle between V phase and I phase. Also, we can calculate it as 3 I phases square are load. But from the power triangle, P equals S cosine phi. Regarding the reactive power, rather than we have a cosine, we can have it as a sine. So Q equals 3 V phase I phase sine phi, or root 3 V line I line sine phi. Also, we can write it as 3 I phases square x load based on the load capacitive or inductive. So Q based on this power triangle equals sine phi multiplied by S. Q can have positive or negative based on the load nature. So this triangle could be up or down. It depends on the load nature. Regarding the apparent power, S equals 3V phase I phase or root 3V line I line. Also, you can calculate it as the 3I phase square multiplied by the amplitude of the impedance. Or you can write S equals root P square plus Q square, as you can see from this power triangle. What will I watch in video number 7? In video number 7, we are going to have an example of three-phase power using calculation and MATLAB Simulink simulation. See you in the next video.